In today's sessions, let us start from chemical reactions of haloarenes. The first reaction we are going to consider is nucleophilic substitution reactions. It's observed that haloarenes are unreactive towards nucleophilic substitution reactions. Haloarenes are unreactive towards nucleophilic substitution reactions. We have to study the reasons for the same. We are going to highlight 4 reasons. Out of that, any 2 are important for your examination. The first reason we are going to consider is resonance effect. I am going to consider the structure of chlorobenzene, and I will go on writing the resonating structures for chlorobenzene. You know, on chlorine, there are 3 lone pairs of electrons. We have already studied as to how to write resonating structures in class 11th. So I'll shift this lone pair of electrons here. Naturally, the pi electrons get shifted here. So I can write the second resonating structure. I'll continue writing the other resonating structures. This is the third resonating structure. I'll go with the 4th one. For that, I'll shift this lone pair of electrons here. The pi electrons get shifted. You have a negative charge, then you have a double bond. On chlorine, you have a positive charge. And the last resonating structure, I'm going to write like this. So the last one is the Kekulé structure of the first resonating structure. So I have written 5 resonating structures for chlorobenzene. From this I can write the resonance hybrid. So when you write resonance hybrid, I'll draw a hexagon like this. You know that the pi electrons are getting delocalized over the hexagonal ring. That's why I'm going to write the dispersal of the negative charge on the benzene ring like this. And if you observe the bond between chlorine atom and benzene ring, you see in the first and the last resonating structure, it is a single bond, while in between these 3 resonating structures have double bonds. In other words, in resonance hybrid, this bond is neither purely single nor completely double. It is in between the 2. I call it as partial double bond character. We have chlorine atom here. On chlorine atom, in first and the last resonating structures, we do not have any charge, but in between these 3 resonating structures have positive charge. That's why this chlorine should have partial positive charge on chlorine. In other words, what I have written here is resonance hybrid. So when you observe the resonance hybrid, you can make out the partial double bond character of chlorine carbon bond which is connected to benzene ring. You know, whenever the bond order increases, bond strength increases, breaking the bond becomes more difficult. It's for this reason, you know, haloarenes are unreactive towards nucleophilic substitution reactions. In short, I can say that the unreactivity of haloarenes towards nucleophilic substitution reaction is due to the partial double bond character of halogen carbon bond due to resonance. The second reason we are going to consider is difference in hybridization of carbon atom in CX bond. Here I have represented the general formula of haloarene, and this is the general formula of a haloalkane. Let's just concentrate on the type of hybridization of carbon atom in CX bond. In case of haloarene, this carbon atom undergoes sp2 hybridization, whereas in case of alkyl halide, the carbon atom undergoes sp3 hybridization. And last year, under periodic properties, you have studied that the electronegativity of an atom also depends upon the type of hybridization. When I consider sp2 hybridization, you know that it has a 33.3% S character, whereas in sp3 hybridization, we have 25% S character. What is meant by 25% S character? You know, in sp3 hybridization, 1 S orbital and 3 p orbitals are involved. So the total number of orbitals involved are 4. Out of that, 1 orbital is S orbital. That's why 1 out of 4 orbitals, it comes to 25%. You know, as the S character increases, the electrons lie closer to the nucleus and they experience greater inward pull. Or in other words, I can say that carbon atom having higher S character is more electronegative. So, in case of haloarene, the carbon atom of the benzene ring, because of higher S character, is more electronegative and will hold the shared electron pair of carbon halogen bond more tightly towards itself. Hence, breaking carbon halogen bond is more difficult in case of haloarenes when compared that in haloalkanes. Let us consider a general haloarene. Imagine the haloarene undergoes ionization. So when it undergoes ionization, I expect a phenyl carbocation and X minus ion. Now, this ionization is favored to undergo SN1 mechanism only if this phenyl cation is more stable than haloarene itself. But when you look at the structure of haloarene, you can make out that you cannot have conjugation over here. It is because the positive charge is already present on a carbon atom involved in the double bond. So resonance is not possible. That's why phenyl cation is unstable. Hence, haloarenes undergoing ionization is not favored. It's for this reason haloarenes cannot undergo even SN1 mechanism. If haloarene has to undergo nucleophilic substitution, we have substrate haloarene and the nucleophile has to approach the benzene ring of haloarene. You know that in haloarene this benzene ring is electron rich. And also you know that nucleophiles are electron rich species. Hence, when nucleophile approaches benzene ring of haloarene, it experiences repulsion. It's because of this repulsion, nucleophile may not approach benzene ring at all. It's for this reason haloarenes do not undergo nucleophilic substitution reactions. Just now I told you that haloarenes are unreactive towards nucleophilic substitution reactions. Hence, if we want to carry out nucleophilic substitution reactions, we have to go for drastic conditions. When I say drastic conditions, I have to go for a stronger reagent, I have to go for higher temperature, higher pressure, and I have to carry out reaction for longer duration. In order to give an example, I will consider the conversion of chlorobenzene into phenol. So in order to carry out this, I am going to use aqueous sodium hydroxide. I will go for higher temperature of 623 Kelvin. I'll employ higher pressure of 300 atmosphere. The reaction is carried out in basic medium. That's why what happens, this chloro group will be replaced by OH group. So we expect the formation of OH group over there. But the problem is, very shortly you are going to study that phenol, benzene ring with OH, is acidic in nature, and whenever an acidic compound is formed in the presence of base, it has to form a salt, and the salt of phenol is one in which the OH group which is connected to benzene ring will get converted to ONA, or in other words, H of OH is replaced by sodium. So what we have obtained here is sodium salt of phenol. We call it as sodium phenate or sodium phenoxide. Now this sodium phenoxide can be subjected to acidification in presence of an acid. Na plus will be replaced by H. We get phenol. And this reaction in which a chlorobenzene is converted into phenol is a method of manufacture of chlorobenzene, and this particular method is called Dow's process. Interesting observation is, as we have more number of electron withdrawing groups like NO2 at ortho and para positions, nucleophilic substitution reactions become less and less unreactive. Or in other words, the reactivity of the benzene ring towards nucleophilic substitution reactions keep on increasing. In order to explain that, let us consider few examples one by one. ಸರ್ ಅದು ರೀಸನ್ ಆದ ನಂತರ ಮತ್ತೆ ಸ್ಟಾರ್ಟ್ ಮಾಡ್ತಾ ಇದ್ದೀನಿ. ಅದು ನಾನು ಮಾತಾಡಿದೆ, ಅದನ್ನು ಕಟ್ ಮಾಡ್ಬೋದಲ್ಲ? ರೀಸನ್ಸ್ ಆದ ನಂತರ ನಾನು ರಿಯಾಕ್ಟಿವಿಟಿ ಇನ್ಕ್ರೀಸಸ್ ಅಂತ ಹೇಳಿದೆ, ಅದನ್ನು ನಾನು ಮಾಡ್ತಾ ಇದ್ದೀನಿ. ಹೌದು. ಸೊ ಆಫ್ಟರ್ 4 ರೀಸನ್ಸ್ ಆಯ್ತಲ್ಲ ಸರ್, 4 ರೀಸನ್ಸ್ ಆದ ನಂತರ ನೀವು ಏನೋ ಮಾತಾಡಿದೆ ಅದನ್ನು ಕಟ್ ಮಾಡಿಬಿಡಿ. ಈ ಸ್ಟ್ರಕ್ಚರ್ ಬರೆಯೋಕ್ಕಿಂತ ಮೊದಲು. ಹೌದು. ಆಫ್ಟರ್ ಆ 4 ರೀಸನ್ ಪಾಸಿಬಲ್ ರಿಪಲ್ಷನ್ ಅಂತ ಇದೆ, ಅದರ ನಂತರ ಏನು ಮಾತಾಡಿದ್ದೀನಿ ಅದನ್ನು ಕಟ್ ಮಾಡಿಬಿಡಿ. ಆಫ್ಟರ್ ಆ ಪಾಸಿಬಲ್ ರಿಪಲ್ಷನ್, ಆ ರೀಸನ್ ಆದ ನಂತರ, ಆ ರಿಪಲ್ಷನ್, ಆ 4th ರೀಸನ್ ಆದ ನಂತರ ಬಿಫೋರ್ ರೈಟಿಂಗ್ ದಿ ಸ್ಟ್ರಕ್ಚರ್ ಏನಿದೆ ಅಲ್ಲ, ಕಟ್ ಮಾಡಿಬಿಡಿ. You know now, haloarenes are unreactive towards nucleophilic substitution reactions. So, ಇಲ್ಲ ಅದು ಅಲ್ಲೆಲ್ಲ ಸರ್, ಎಲ್ಲಿ ಕಟ್ ಮಾಡಬೇಕಂದ್ರೆ ಒಂದು ನಿಮಿಷ, ಅದು ಡೌಸ್ ಪ್ರೊಸೆಸ್, ಡೌಸ್ ಪ್ರೊಸೆಸ್ ಆದ ನಂತರ, ಹೌದು, ಡೌಸ್ ಪ್ರೊಸೆಸ್ ಆದ ನಂತರ ಇದನ್ನು ಮಾಡಿಬಿಡಿ. ಪಾಸಿಬಲ್ ರಿಪಲ್ಷನ್ ಬೇಡ, ಪಾಸಿಬಲ್ ರಿಪಲ್ಷನ್ ಇರಲಿ, ಅದು ಪಾಸಿಬಲ್ ರಿಪಲ್ಷನ್ ಆದ ನಂತರ ಇರಲಿ. ಡೌಸ್ ಪ್ರೊಸೆಸ್ ಆದ ನಂತರ ನಾನು ಇದನ್ನು ಹೇಳಿದ್ದೀನಿ, ಏನು ವಿತ್ ದ ಪ್ರೆಸೆನ್ಸ್ ಆಫ್ ಎಲೆಕ್ಟ್ರಾನ್ ವಿಡ್ರಾಯಿಂಗ್ NO2 ಗ್ರೂಪ್ಸ್ ಅಂತ ಹೇಳಿದ್ದೀನಿ, ಅದನ್ನು ಕಟ್ ಮಾಡಿ. So you know now, haloarenes are unreactive towards nucleophilic substitution reactions, but it is observed that electron withdrawing groups like NO2, whenever they are present at ortho and para positions, the haloarenes become more and more reactive towards nucleophilic substitution reactions. In order to provide evidence, I have considered these 3 chlorobenzene derivatives. In the first example, we have only one NO2 group at para position. If you look at the conditions, temperature is reduced to 443 Kelvin and the reaction is carried out at 1 atmospheric pressure. I'll move over to the second example. We have 2 NO2 groups, one at ortho position, the other one at para position. Here the reaction conditions become still milder. Temperature is lowered from 443 Kelvin to 368 Kelvin. And finally, when both the ortho positions and one para position are occupied by NO2 groups, if you observe the reagent, we are not using even sodium hydroxide. It is just water and we just need to warm it. Nucleophilic substitution reaction takes place to form the corresponding phenol. So from these examples, it's clear that with the increase in number of electron withdrawing groups like NO2 at ortho and para positions, haloarenes become more and more reactive towards nucleophilic substitution reactions. Now let us find out the reason as to why the presence of NO2 group increases the reactivity of chlorobenzene towards nucleophilic substitution reactions whenever they are present at ortho and para position. If you just look at the mechanism here, this is the nucleophile OH minus which attacks the carbon atom of the benzene ring carrying chloro group. So in the first step, you can observe that the negative charge is present on the carbon atom carrying NO2 group. In other words, whatever intermediate formed here is nothing but carbanion. It is carbanion. If this carbanion has to be stabilized, this negative charge has to be dispersed. Here on the carbon atom carrying negative charge, you have a powerful electron withdrawing group in the form of NO2. So this NO2 group withdraws the excess electron density towards itself. As a result, the negative charge on this carbon atom is dispersed. The stability of this carbanion increases, or in other words, this reaction proceeds in the forward direction. In the same way, if we have NO2 group at para position, from these resonating structures you can make out that the negative charge is present on para carbon atom, and on the para carbon atom you have electron withdrawing NO2 group. Again, this negative charge is dispersed effectively. Stability of this carbanion is increased. Hence, the reaction proceeds in the forward direction. So, because of this, I can say that whenever we have electron withdrawing groups at ortho and para position, the resultant carbanion is stabilized because the electron withdrawing group causes the dispersal of the negative charge effectively. If the electron withdrawing group is present at meta position, you can observe in these two resonating structures that the carbon atom carrying NO2 group will not have negative charge at all. In other words, in the meta position, we do not have negative charge. Where do we have negative charge? At ortho and para position. So, negative charge is present at ortho and para position, but electron withdrawing group is present at meta position. That's why NO2 group is not very effective in causing the dispersal of the negative charge. In other words, the stability of carbanion is not increased. It's for this reason the reaction does not proceed in the forward direction favorably. It's for this reason, presence of NO2 group at meta position does not increase the reactivity of haloarenes towards nucleophilic substitution reactions.